Hello and welcome. Today we'll be introducing the conservation of energy. First we'll cover some definitions, then go into what conservative and non-conservative forces are, and lastly, derive some formulas. The law of conservation of energy states that energy cannot be created or destroyed. It is conserved and can only be changed from one form to another. If the work done by a force that moves an object from A to B does not depend on the path taken, then we call it a conservative force. Every conservative force has potential energy associated with it. For example, gravity has gravitational potential energy, and spring force has elastic potential energy. Forces like friction, which dissipate energy instead of storing it, are called non-conservative forces. Overall, the work that is done depends on the path taken. For example, friction creates thermal energy, which removes energy from the system. This cannot be fully converted back to work, hence it is called non-conservative. Next, we'll be deriving the following formulas.
Welcome back. I'm now going to introduce you to the concepts of work.
Thank you, Sal, but we'll take it from here. The work energy theorem states that the net work done by the forces on an object is equal to the change in its kinetic energy. This does not apply to the work done by a single force. We use the standard formula used to find work and substitute force with mass times acceleration. Acceleration is isolated from v2 squared equals v1 squared plus 2ad, which gives us the final formula. The work energy theorem states that the net work done by the forces on an object is equal to the change in its kinetic energy. Gravitational potential energy is stored energy due to height in a gravitational field, where m is mass in kilograms, h is the height above the origin in meters, and g is the acceleration of gravity. Kinetic energy is the energy that an object has due to its motion. Overall, it can be described using the work energy theorem, but we've extended the formula to apply to situations where the object starts from rest. Thus, V1 is eliminated.
In a frictionless environment where all energy is conserved, one can observe the beauty of the conservation of energy. Since no energy is lost, the total energy held by a system is constant throughout time. This can be demonstrated through an example of a skater. Notice how the skater starts with the kinetic energy of 0 and the gravitational potential energy of approximately 3,867 joules. Then, when the skater reaches the lowest point, all the gravitational potential energy is turned into kinetic energy. Finally, when she reaches the other side of the ramp, her kinetic energy and velocity is 0, while her gravitational potential energy is back to approximately 3,867 joules. From then on, she will skate down the ramp until she reaches her original position, where she will then repeat the same motion unless an external force acts upon her. This can further be exemplified with a more drastic track, but since there is no friction in this case, the skater will be able to reach the other side due to all of the energy being saved and converted back into gravitational potential energy at the end of the track.
Friction is an example of a non-conservative force that changes mechanical energy into thermal energy. From what we've applied in class, thermal energy is simply the work done by frictional force. In this case, it is negative because heat dissipates, thus being removed from the system.
In an environment with friction, the total kinetic and potential energy of a system is non-constant throughout time. Since some energy is lost through the conversion to heat, from friction, and sound, over time the system will lose kinetic and potential energy until there is no more energy left. Like the previous example, the skater starts with a gravitational potential energy of approximately 3,867 joules, and a kinetic energy of 0 joules. But when the skater reaches the lowest point, not all of her gravitational potential energy is turned into kinetic energy. This is because of how some of it is converted into thermal energy, meaning that the speed will be lower than it is in the first example. The skater also doesn't reach the same height as before because the remaining kinetic energy won't be enough to reach that, coupled with the additional loss of energy from friction. Gradually, the skater will reach lesser heights and speeds until the point where she has a total energy of 0 joules. As stated earlier, when only conservative forces act on or within a system, the total energy is a constant, which in this case refers to gravitational and kinetic potential energy. When both conservative and non-conservative forces come into play, energy conservation can be applied and used to calculate motion in terms of the known potential energies of conservative forces and the work done by non-conservative forces. Let's summarize it all with another example. We can start by putting our skateboarder in an environment with non-conservative forces acting on the skater. and also make the path more exciting. You can see how she moves up and down the path until she reaches the end, but her kinetic energy and velocity is lower than what it should have been if instead she rode a relatively straight line. This is because of the increased distance she must travel, meaning there is more contact time with the track, which causes losses of energy due to friction. The conservation of energy can be applied here to find out what amount of energy was turned into thermal energy. We start by analyzing the speed of the skater in meters per second when she leaves the track. Using GIMP, I can calculate that the skater leaves the ramp at approximately 4.7561 meters per second. Then, to solve for the thermal energy, I use the formula initial kinetic energy plus initial gravitational potential energy plus work done by non-conservative forces is equal to the final kinetic energy plus the final gravitational potential energy. After subbing the values in, I can determine that the work done by non-conservative forces is negative 3153.5 joules. Since work is negative, this means that much energy of the system was lost due to friction. In real life, however, other non-conservative forces include sound and air resistance, to name a few.
Here we have a beautiful question involving friction, ramps, and a box. First, the box goes down a ramp, then slides across the surface and soars off the edge in projectile-like fashion and falls onto the ground. How far does it travel? Well, first we're going to develop an equation to represent this problem. The problem begins with only gravitational potential energy at A. As it slides down to B, thermal and kinetic energy alike is produced. The same occurs as it approaches C. Therefore, we're left with a final equation which states that the gravitational potential energy at A is equal to the sum of the kinetic energy at C, the thermal energy produced from A to B, and the thermal energy produced from B to C. Then we're going to expand the equation and rearrange for the velocity of the box at C. Yada yada yada, plug in the values, square root, bam. We get the velocity to be 4.36107 meters per second. To find the distance, we need time. To find time, we use dy equals to v1t plus 1/2 at squared. Rearrange and plug in the values to get 0.71961 seconds. Lastly, we use d equals vt to find the final distance traveled by the box, which ends up as 3.14 meters.
The lab we chose to perform involved the skateboarder, with the intent of finding out whether the theoretical values would match the simulation values. We chose the physical quantities of mass, time, length, and speed, and we also assumed that the mass of the skateboarder was 75 kilograms. We took the speed of the skater at half-second intervals to see how the kinetic energy changed in relation to the gravitational potential energy.
In the first frictionless environment, we saw that there was in fact the expected amount of both energies at any point in time in the system. In the environment with friction, we also saw that the energy of the system went down over time due to non-conservative forces, being friction in this case, causing the energy of the system to go down over time.
Both of the simulations supported the theory, as the gravitational potential energy went down when the kinetic energy went up, and vice versa. If you added up the heights of each type of energy at any time period on the graph, it would equal the total amount of energy in the beginning, proving that the total energy of a system is always constant.
Elastic potential energy is energy stored as a result of applying a force to deform an elastic object. Work is done when the object springs back to its original position, whether the deformation be from compressing, stretching, or twisting the object. An object designed to store elastic potential energy, such as a rubber band, coiled spring, or a bow, will typically have high elastic, but all elastic objects will have a limit. First, we will introduce a formula to calculate the elastic potential energy for an ideal spring. To calculate the work done to stretch or compress a spring that obeys Hooke's law, we need an expression for the potential energy stored in the spring. Hooke's law states that the magnitude of force F on the spring and the resulting deformation delta L are proportional. For our spring, we will replace delta L, which is the deformation caused by force F, with distance x, which represents how much the spring is stretched or compressed. Since the force increases linearly from 0 to kx, the average force is kx by 2. Therefore, the potential energy of a spring is equal to 1/2 kx squared, where k is the spring's force constant and x is the displacement from its undeformed position. Here you can see the equilibrium point at the dashed line. When the spring is stretched to its maximum below the equilibrium position, you can see that the elastic potential energy is at its maximum, where it is greater than the gravitational potential energy, which is what brings it back up. In contrast to this, when the spring is compressed above the equilibrium position, its gravitational potential energy is at its greatest, making up the total energy in the system. At both these extremes, you can see that there is no kinetic energy, as it is essentially changing directions as it oscillates back and forth. The explanation from the first demonstration applies here as well. However, due to the damping of the spring, which is the restraining of vibratory motion such as oscillations and noise, part of the energy is converted into thermal energy. Due to this, the mass in the spring reaches mass equilibrium point much quicker, and a portion of the energy remains lost as it dissipates in the form of heat. On the very left, we have the spring with spring constant k at its natural length. In the middle, we have a spring with mass attached at its new equilibrium point where the net force on the mass is 0. It is the distance a from the natural length. The spring force kx minus the gravitational force mg is equal to 0. We isolate for x the distance from the original point, which is mg over k, equal to a. If we pull it down beyond the new equilibrium position by distance b, the spring is pulling up with more force than the force of gravity, which brings it up and beyond the equilibrium position. There, the spring force is less than the force of gravity, and it goes back down, back and forth, causing it to oscillate. Let's figure out how much energy there is in the system from the start. Using conservation of energy, we will set the initial equal to the final. Here we use the elastic potential energy formula that we derived earlier. The distance deformed is not only the new equilibrium position, but from its natural length too, which makes it a plus b. The reference point for the gravitational potential energy is up to us, so we make it the lowest point, and because h is 0, mgh is 0. At its equilibrium position, the amount stretched is equal to a, which makes it 1/2 k squared. Slap on the kinetic energy that it has going up at that point, as well as the gravitational potential energy, where h is b, the distance stretched from the equilibrium position. To solve for v, we have to untangle this mass that we have to the left. First, we expand. Then we expand some more. Then we realize that, hey, we can cancel some things out, so we do. On the left side here, we recognize that aka is equal to mg from the beginning, where we found the distance between the equilibrium point and its natural length. So we slap that on, and wow, would you look at that, it cancels out even more. Finally, you're left with this beautiful and simple equation. Basically, if you measure the spring displacement from the new equilibrium position, you wouldn't even need to mention gravitational potential energy because it all just cancels out, leaving you with the same answer. Gravity simply shifts the equilibrium position down a bit, and the mass and spring would behave just as it would on a horizontal surface.
Glad to see you're still with us. In this video, we covered the conservation of energy and the different kinds of forces like conservative and non-conservative. Not only did we derive some exciting formulas, but we even simulated some really exciting scenarios to show off how this equilibrium plays a part in our daily lives. On top of that, we learned about springs. We introduced elastic potential energy and showed off why horizontal and vertical springs are treated the same way in calculations. We did more simulations, an example, and here we are. We can do so much with the potential we have here. Catch you next time!